In this video, we're going to talk about gas diffusion in the lungs specifically. And there are a few things that affect gas diffusion. Temperature matters, but we don't really have to care about it too much because it's constant or close to constant in a person. Surface area, again, matters, but unless you have COPD and your lung volume is going down, that should be relatively standard. We want the surface area to be high. Just in a healthy person, it doesn't really change. The thing that really matters that we have to change or worry about regulating is the difference in partial pressure between blood and air. So we should probably talk a little bit about what partial pressure actually is. Air pressure is measured in millimeters of mercury. It is a very old-fashioned, kind of ridiculous way to measure pressure because that's how old-fashioned barometers used to work. You would have a glass tube filled with liquid mercury, and you measured the pressure by how high it pushed the mercury up the glass tube. Okay, so the total pressure in the atmosphere at sea level is about 160 millimeters of mercury, and of the air that's in the atmosphere, approximately 78% is nitrogen, 21% is oxygen, and a very tiny amount, a fraction of 1%, is carbon dioxide. Okay, partial pressure, right? So when we say the atmospheric pressure, the PO2, the P stands for partial pressure of oxygen, is about 160. All that means is if you take the total pressure of 760 millimeters of mercury and you multiply it by 0.21, you get approximately 160 millimeters of mercury. That is your partial pressure of oxygen. It basically means since O2 is 21% of the atmosphere, it's responsible for 21% of the total pressure, and 21% of 760 is 160. In practice, a partial pressure is very, very similar to a concentration. It's basically the equivalent of a concentration for gases. But instead of molarity or like grams per liter or whatever, we measure it in millimeters of mercury, partial pressure. All right, so a rule is just like molecules diffuse from high to low concentration, gases are going to diffuse from high to low partial pressure. And the important follow-up to that is you can have partial pressures in both air and in liquid. And so the air you're breathing has different partial pressures. The water that you drink from a glass has partial pressures of oxygen and nitrogen. And so does your blood. Okay, so if this is air coming in an alveolus, right, our partial pressure of oxygen from the air is about 160 millimeters of mercury. The partial pressure of oxygen in your alveoli is never going to be that high just because, remember, your lung volume never goes to zero because you have residual volume. And so when that 160 from the atmosphere mixes with the sort of old stale air, the residual air in the lungs that's been there for a while, it's going to dilute it and go down a little bit. So about 120. Now, the blood from your pulmonary arteries coming in, which remember is low oxygen because we haven't got to the lungs yet, probably has a PO2 of somewhere around 40. That number can go down a little bit if you're exercising, but for a person at rest, around 40-ish, right? That sets up a gradient, right? 120 is obviously higher than 40, and so I'll draw this as a slope, right? We have a slope of oxygen diffusion from high to low, right? Going from high concentration in the lungs to relatively low concentration in this blood. And so by the time the blood leaves the lungs, it'll wind up having a PO2 of somewhere around 100, maybe upper 90s, low hundreds. Again, depends on how fast the person's breathing. Are they exercising? All those variables come into play. Right? If you breathe faster, you can make this number go up a little bit. Right? Like hyperventilating would make that number go up because you're taking more of that 160 air into the lungs. Hypoventilating or breathing slowly could make that number go down because you're taking in less of that air. Right? The same exact thing works in reverse for CO2. Right? CO2 is incredibly low in the atmosphere, less than 1%. And in the lungs, it's relatively high. The reason for that is your tissues, your entire body, your organs are making CO2 as a waste product. Right? And I know the numbers seem like they're really close together. It has to do with the way that CO2 is buffered and transported in the blood. But just sort of take my word for it right now. If CO2 comes into the lungs at a PCO2 of 45 millimeters of mercury, obviously 45 is higher than 40, which is about where it sits in the lungs, you get a gradient in the opposite direction. Right? Now you have high in the blood, low in the lungs. If you breathe faster, remember, that means that you're breathing in more of this low CO2 air. So hyperventilating would actually make your CO2 go down. Right? That's going to give you faster diffusion because it effectively lowers the low end of your gradient, right? And makes a steeper downhill slope. And so just like breathing faster raises the high end of the oxygen gradient, steeper slope, breathing faster lowers the low end of the CO2 gradient, also steeper slope. And so if you breathe faster, you're going to get faster diffusion of both oxygen and CO2, just in opposite directions, right? Oxygen into the blood, CO2 out of the blood, right? Another thing to remember is that all of this is going to be reversed if you go out to cells somewhere else in the body, right? We have this high oxygen, low CO2 blood coming out of the lungs, right? I'm not going to draw a heart, but imagine we go through the heart and we come out the aorta, and now we're cruising out into circulation. These are representing cells, any organ, it doesn't matter. Kidneys, livers, skin, bones, muscles, they're all the same for this purpose, right? Since we have relatively high PO2, right, somewhere around 100, PO2 inside of your cells when they're at rest lives in about that 40 range. Now we have a high to low gradient this way. Oxygen is going to leave the blood as you move through the capillary, right? This is a capillary bed. You expect oxygen to continue to leave, and so maybe it'll go down to 80, 70, right, 60, keep getting lower and lower the further over we go, right? And at that point, now we're basically looping that back to the vena cava to go to the right side of the heart, back to the pulmonary arteries, back to the lungs to get reoxygenated, right? And so there's always going to be gas diffusion in tissues. If you are anywhere in the systemic circuit, right, it's going to look like this: oxygen leaving. If you're in the pulmonary circuit in the lungs, oxygen entering. Right? Same concept for CO2. Back at the lungs, CO2 left the blood, entered the alveoli because we're breathing it out. In these cells, they're making CO2. Right? They're basically a little CO2 factory because CO2 is a normal waste product of cellular respiration. And so your CO2 comes in at 40. It only goes out at 45 because a lot of the CO2 is transported as bicarbonate or bound to hemoglobin. And so the actual PCO2 doesn't go up much because the CO2 gets stored in other ways, but it's there. CO2 is going from high to low now into the blood. All right, so we're at a higher level when we leave. Same deal to the vena cava, to the right side of the heart, to pump back through the pulmonary arteries to the lungs. Release that CO2 into the alveoli and breathe it back out into the atmosphere. All right. The last thing to tie into this topic is asking, okay, how are those gases actually transported? And the answer is on hemoglobin. All right. So remember, hemoglobin is actually just a protein that consists of 4 subunits. Right. So 4 globin proteins with a heme at the middle. I'll make my green circles representing heme. They can each bind 1 oxygen, right? Red dots are oxygen. And the question is, how much oxygen can we transport bound to heme? So this concept, hemoglobin, we abbreviate HB. If hemoglobin is bound to oxygen, we call that saturation, right? The binding of oxygen to hemoglobin means the hemoglobin has been saturated. That is exactly what the y-axis in these graphs is going to be showing us. What percentage of these binding sites are full of oxygen and what percent is empty. And so if the graph says saturation is 90%, it means 90% of those binding sites have an oxygen on them and 10% don't, right? You can also have some oxygen just floating in the fluid of your plasma. That's PO2, right? That is the x-axis, oxygen partial pressure, right, in the plasma. Right, so main point is your oxygen can exist in 2 different states. It can be floating around in your plasma, just dissolved in water. That's PO2. Or it can be bound to hemoglobin. that's saturation. Right? All this graph is showing you is that as the partial pressure of oxygen goes up, if there's more oxygen dissolved in your plasma, then saturation is going to go up. Okay? And so partial pressure of oxygen determines saturation. Right? These values out here, this is what you would expect to see in your lungs. High partial pressures, which means high saturation in the 90%, 90 to 100% range. Right? As blood moves out through the systemic circuit, you expect that PO2 to go down once you hit capillary beds because capillaries let oxygen diffuse across their thin walls, and your organs are going to start using it. Right? And so if we pretend that, let me clear this off a little bit. Let's say that we started in the lungs in a normal healthy person, and we started off with a PO2 of around 100. Typical, we're going to follow the blue line because that's normal conditions. And they had a saturation of, let's say, 97%. So 97 filled with oxygen and 3% weren't, right? As you go into the systemic circuit, let's say that you're at rest. 40% is about a normal level for a resting person. Come up to our blue line, go over, and let's say that's 72%. Right? What that means is that you had hemoglobin letting go of 25% of its oxygen, right? 97 down to 72. That was used by tissues. If you start exercising, maybe you'll go down to 20%, right? That would bring your saturation down to, let's say, 35. That means you let go of more of your oxygen. Work harder, run faster, go down to 10. That breaks us down to a saturation of maybe 9%. And so the further you push, right, work harder, exercise more, your oxygen partial pressure is going to go down, go down, go down. The further it goes down, the more the hemoglobin releases that oxygen for those muscles to use for the workout, right? And then, of course, on the way back up, you stop exercising, you start breathing faster, or keep breathing faster. You take in oxygen, but you're not exercising anymore. That lets O2 levels go back up. Your saturation goes back up, and you can get back to normal. Right. All that works perfectly fine, but we can change a few things. Right. These other lines on here, the green and the red line, are showing you what happens if your pH changes. If your pH becomes more acidic, right, from 7.4 is normal, 7.0 is a little bit more acidic than you should be, 7.8 is more alkaline or basic than you should be. If you become acidic, which happens when you start overproducing CO2, so if CO2 levels go up, it'll make your blood pH a bit acidic. What that means is the whole curve sort of shifts down and to the right. And as an example, let's pretend that we're at this 30 mark for partial pressure. Under normal pH conditions, you have a saturation of about 65% when PO2 is at 30. The red line that shifted, your saturation goes down to only 30%. Huge drop off. So what this basically is telling you is high CO2, right, acidic pH, and heat can do the exact same thing. They all push oxygen off of hemoglobin, right? So if your CO2 goes up, you become acidic, or if you get hot, all of those things remove oxygen so that even at the same partial pressure, your saturation goes down. The flip side, if you have low CO2 or your tissues are relatively cold, or you become alkaline, right, and low CO2 and alkaline go together, that shifts the curve the other way so that you bind more oxygen. That's perfect, because the place where you're most likely to be cold and have low CO2 is the lungs. Saturation goes up. The place where you're likely to be hot and acidic and have a lot of CO2 is in an exercising muscle. Perfect. Saturation goes down. That's actually a good thing because it means that hemoglobin is letting go of more of the oxygen for the muscle to actually use. All right, I think that's a good stopping point for this video. Follow along to the next one in the playlist, and we'll talk a bit about VO2 max and the limits of oxygen transport.